Welcome back, Focus learners, to another Explainer. Today, we're unraveling a fascinating and honestly, a notoriously stubborn mystery in material science. We're talking about the massive mismatch between what textbook physics tells us should happen and the physical reality engineers actually face every single day. We're zeroing in on Fermi-level pinning in organic semiconductors. If you've ever wondered why simply swapping out a component in an organic electronic device doesn't magically give you the energy alignment you'd expect, well, you're absolutely in the right place. Let's get into it.
Okay, let's dive into the core problem right off the bat. Here's the expectation. You want to change the injection barrier in your device. Maybe you're working on an OLED screen or a new solar cell, so you figure, I'll just swap the metal electrode for one with a different work function. Sounds super simple, right? But reality has other plans. The interface actually fights back. When you change that metal, the organic layer creates its own electrostatic adjustment. It forms this interface dipole that essentially just eats up your electrode's work function. So yeah, your simple swap doesn't magically fix the energy alignment at all.
To really grasp this, check out the contrast between the ideal picture and the reality. In a perfect textbook world of vacuum-level alignment, where there are no chemical reactions or charge transfers, you just pick your electrode and you directly tune how easily holes or electrons get injected. The vacuum levels just beautifully line up. But in reality, notice that sudden sharp drop at the interface? That right there is the interface dipole shifting the rules of the game. The organic semiconductor doesn't even see the bare metal work function anymore. It sees an effective interfacial work function. A huge chunk of your intended energy shift is literally just canceled out by this dipole.
Moving on to Section 1, Unlearning Silicon, the Organic Matrix.
To truly understand why this interface dipole happens, we kind of have to shed our old assumptions. If you're coming from a background in traditional, rigid, inorganic electronics, you basically have to unlearn silicon. Organic devices just do not play by those same crystalline rules. Let's walk through this comparison. With inorganic semiconductors, like silicon, we're used to talking about delocalized conduction and valence bands, where charge carriers move in nice, broad waves. And pinning there? That's usually caused by surface states or dangling bonds. But look at the organic column. Organic semiconductors rely on HOMO and LUMO-derived states. Their charge carriers are highly localized. They literally hop from molecule to molecule as polarons. Because of this fundamental structural difference, the main causes of pinning completely shift to things like charge transfer and density of states tails. And that makes their injection barriers remarkably insensitive to whatever electrode work function you try to choose.
Section 2, Anatomy of an Interface, the Mechanisms of Pinning. So what is physically happening at that microscopic boundary to cause all this stubbornness? Well, we aren't just dealing with one rogue variable here. There are actually 5 distinct mechanisms that can cause pinning: integer charge transfer, gap or tail states, metal-induced states, the pushback or pillow effect where electron clouds physically compress, and chemical hybridization. Any single one of these, or a messy combination of them, can trigger that interface dipole. So let's zoom in on the 2 biggest culprits.
The first major mechanism is integer charge transfer. In this model, the organic molecules right at the interface literally exchange complete electrons with the metal electrode. And they do this until the energy cost simply becomes too high to keep going. When a molecule loses an electron, it becomes a positive polaron. When it gains one, it becomes a negative polaron. And these molecular ions act as powerful, highly localized electrostatic anchors. They effectively pin the interface Fermi level right at their specific energy states. No moving past it.
And this gives us 3 distinct alignment regimes. On the left side, in regime 1, if you use a very low work function electrode, negative polarons form and you are pinned low. No matter how much lower you go with your metal, that barrier barely changes. On the right side, in regime 3, with a high work function electrode, positive polarons form and you are pinned high. Again, you hit a total wall. It's only in that middle sweet spot, regime 2, where vacuum alignment actually holds up and your tuning works. But as you can see, that window is severely limited.
The second major mechanism is what we can call the DOS sponge, or density of states sponge. Textbooks absolutely love to draw energy levels as these sharp, perfectly defined lines, which is beautifully optimistic but physically completely wrong. The physical reality is that structural disorder in the organic material broadens these energy levels out into sweeping tails. These tail states act exactly like a chemical capacitor. If the Fermi level moves into this tail region, those states just soak up the charge like a sponge, fiercely resisting any further movement.
Let's move to Section 3, Quantifying the Trap, Measuring the Pinning Effect.
So, how do engineers actually deal with this in the lab?
Enter the pinning factor, denoted by the letter S. You can think of this as the ultimate scorecard for how much control you actually possess over your device's energy alignment. It mathematically quantifies how much the injection barrier changes when you tweak your electrode work function. If S equals 1, you've got weak pinning. The barrier perfectly follows the electrode. Awesome! But if S equals 0, you have strong pinning. The barrier is totally trapped, and changing the metal does almost nothing.
Think of it kind of like a dial, driven by the balance of capacitance. The core equations show us that S is basically a ratio involving geometric capacitance and that DOS capacitance we just talked about. If the DOS capacitance is high, meaning there are just tons of tail states soaking up charge, it acts like a heavy weight, yanking the S factor needle all the way down towards 0. In that red zone of strong pinning, your barrier is barely moving, no matter how hard you try turning the knob on your electrode work function. So, the crucial point here is perfectly captured in this numerical autopsy of a failed metal swap. Imagine an engineer upgraded from electrode A with a work function of 4.2 electron volts to electrode B at 5.0. Ideally, that massive 0.8-fold jump should have dropped the whole injection barrier down to a beautiful, highly efficient 0.4 electron volts. But reality bites. The barrier only marginally improved to 0.6. Why? Because the interface formed a dipole and greedily consumed the rest of that precious energy shift.
Section 4. Real-world stakes. Device consequences.
Now, you might be wondering, why does a fraction of an electron volt even matter? Let's bring this microscopic math back to macroscopic reality and look at the real-world stakes across 3 major technologies. In organic OLEDs, or OLEDs, the screens in our high-end phones and TVs, unfavorable pinning at the contacts artificially drives up the turn-on voltage. That ruins power efficiency and absolutely drains your battery. In organic solar cells, it's a bit of a double-edged sword. Pinning can help selectively collect charges, but if it goes wrong, it creates massive extraction barriers that cause severe energy loss. And in organic field effect transistors, pinning introduces severe contact resistance bottlenecks. So you can't just pick a better metal to make the transistor run faster, the interface dictates the speed.
Before we wrap up, we really need to finalize our paradigm shift by busting 3 major myths. First, we have to stop picturing HOMO and LUMO as sharp, perfect textbook lines. The reality is messy. They're broadened into distribution tails by disorder and microscopic defects. Second, interface dipoles aren't inherently evil. In fact, modern engineers use interlayers to deliberately create dipoles and modify the effective work function to their advantage. And third, maybe the biggest myth of all, throwing a higher work function electrode at a problem does not automatically lower your whole injection barrier. Once you are pinned, increasing that metal work function mostly just pumps up the interface dipole, achieving absolutely nothing for your actual device.
And this brilliantly illustrates our ultimate takeaways. Think of it as your interface engineer's cheat sheet. Keep these core equations handy. The absolute fundamental rule you must remember is that Fermi-level pinning partially fixes the effective electrode energy relative to the HOMO and LUMO levels. Changing the metal work function does not fully control charge injection. You are dealing with a highly active dynamic interface, not just a passive geometric boundary.
Which brings us to our final challenge. You now know the textbook is a massive simplification. You know the DOS sponge and integer charge transfer are just waiting there to trap your Fermi level. So if the organic interface always fights back, how will you choose to engineer the dipole of tomorrow's devices? Will you keep fighting the physics, or will you use these principles to actually master the interface? Thanks for joining me on this explainer. Keep asking those great questions, and I'll see you in the next one.